She's the Leonardo Assistant Professor at CMU, and she's done a lot of very interesting work at the intersection of machine learning, game theory, security games, and even sustainability. And she's also like a co-organizer of the workshop. And today she'll be talking to us about reinforcement learning for complex security games and beyond. Thank you so much, Faye, and the floor is yours.
Thank you. And good afternoon, everyone. It's a pity that I cannot be there in person. I hope that I can resume at least national travel soon. International ones probably still are on hold. Now, starting from this week, CMU is allowing people to not wearing masks on campus. So it seems like things are going back to the normal mode. So today I'm going to talk about our work on reinforcement learning for complex security games and beyond. We are particularly interested in challenges in security and environmental sustainability, and whether the security is in the physical world, in the cyber world, or in the case of like environmental sustainability, where the law enforcement agencies is trying to fight against people who are doing illegal logging, illegal poaching, or overfishing. We do see this defender-attacker type of interaction pattern, and we want to see how we can leverage AI to address those problems. In the past more than a decade, there has been some successful attempts to handling this using machine learning and game theory, including my own work. In the earlier days, we've worked on using Stackelberg security game model to model the problem of protecting the ferry lines. Like this is a Staten Island ferry in New York. It's a straight line for the ferry to move along, and the Coast Guard people are worried about the potential attacks that has happened to other big boats in the past, where there's a small boat packed with explosives and then run into the big boat. So we modeled this as a Stackelberg game where the defender is the leader and the attacker is follower. And our goal here is to find out a strategy for the defender, which is a probability distribution over multiple patrol routes, so that we can minimize the attacker's maximum expected utility. So here we can write down the payoff matrix with each row representing a possible route for the defender, each column representing one possible attack time and target for the attacker, and then try to figure out solve this game through mathematical programming and figure out the best probabilities for each of the routes. And we did this, and we made some improvements by using flow-based representation and solve the linear program to get the optimal defender strategy. And in the in-lab experiments, we showed that it can indeed reduce potential risk, and this was deployed in the field since 2013. And here, the feedback we get from the Coast Guard is that they feel that this game theoretic solution indeed increased the randomness, and there has been some reports saying that our work together with the optimization for protecting other parts of the port has led to $33 million saving in 10 years for the Coast Guard to achieve the same security level, and it continues to impact the Coast Guard patrol policy even now. So that's the Stackelberg security game model's success for protecting the ferry line. And later on, as we moved to the environmental sustainability domain, we started to build new models, the green security game model, for handling this type of problems. Comparing to the ferry protection domains, in this case, we actually got a lot more data describing the poaching activities happened in the past. And in this case, we really want to not only reason about the perfectly rational attacker, but probably more importantly, reason about the human behavior in this case. So we started to build machine learning models to try to model the bounded rationality of the poachers. We've tried various versions of the machine learning methods, have an ensemble model, and use both supervised learning and unsupervised learning all together to get this prediction of the heat map. And it was successfully led to this field test in Uganda and China, where the rangers were sent to the locations that are predicted to be hotspots, and they found a large amount of poaching activities, which is even larger than what they typically find. And actually, as you can see here, this is me holding the snares we found in just one day. It's 22 snares in one day. That's a lot comparing to what they typically find. And also what we found is that in the areas that are predicted to be high poaching threat areas, we found many more snares comparing to the areas that are predicted to be low threat areas. So this all shows that the machine learning model is able to have a reasonable understanding of the poacher's behavior. And building upon these behavior models, we still want to plan the patrols. In this case, we again try to formulate this problem through mathematical programming. And here, the variables are the patrol efforts that we want to spend on different areas. And we want to maximize some objectives. For example, it could be just maximizing the total amount of snares being found. So here we have the machine learning model, and then we can use a piecewise linear function to approximate what the machine learning model tells us. And we can solve this mathematical program and bring this to solve this problem to get the patrol routes. And later on, when we try to bring these to the real world, we also notice that we may also need to take into account the terrain information, not just like you go from this location to this location through a straight line, but really to figure out how the terrain is like and generate patrol routes that are compatible with the terrain by connecting those terrain features like ridge lines, streamlines all together, and then design the patrol routes on this so-called virtual street map. So this led to the field test in Malaysia, where again, people found all kinds of animal activity signs and human activity signs. So now this whole thing, the prediction of the poaching threat together with the planning of the patrol route has been successfully integrated into a software called SMART, which is a spatial monitoring and reporting tool supported by multiple global conservation agencies and used by more than 600 conservation sites worldwide. And some parks are already using it to predict poaching threat, and there hopefully will be more field tests on the way. So we are all excited about these successful field tests and deployments of security game models and green security game models. And these tests, in turn, reveal a series of new research challenges. And in the past few years, we have been developing new AI techniques to tackle these challenges. For example, how to design patrol routes that are adaptive to real-time information, such as footprints found by the rangers. So I'm going to talk about these challenges one by one. So for this first challenge, it is actually motivated by a conversation with the site managers. They told us that they don't necessarily always stick to the pre-planned patrol routes, because if they found footprints and they know that these footprints don't belong to them, they would try to react to it sometimes. And I was asking them, how can you tell that the footprints don't belong to you as the rangers? And then the site managers told us that in some sites, the ranger team can sometimes purchase a special type of boots so that the footprint is very distinctive, so that if they observe the footprints and it's not belonging to the ranger team, then they know this is from the poachers. So if they found this, then they would decide whether they're going to chase the poachers or not. And there's some complications here in the sense that if this is an area that they have a lot of rangers and they know that the poachers are not well equipped, meaning there's no guns in the poachers' hands, then they would try to chase them. But in some other cases, they were worried about the poachers having guns. Then if they see the footprints, they may even avoid the actual contact with the poachers by taking a different path. So anyway, so there is a chance that they would react to the real-time information. So clearly, the mathematical programming-based approach that we developed before in the green security game, it cannot adapt to this more complicated case. So we instead model the problem as a Markov game in the grid world. We build a new game model. In this game model, the rangers starts from the patrol post, the starting point in the middle of the grid here, and the poachers would move in this grid, and the poachers can also place snares in some of the snares as they see fit. And the rangers are also moving in this grid, and both rangers and poachers can leave footprints in the grid cells as they walk, but they can observe only the footprints in the cells that they are in. So here we assume that they can differentiate the footprint from themselves and the footprints of others. And besides, each grid cell might have a bunch of features like animal density and other type of features. So our goal here is to find out what would be a good strategy for the ranger to use in this patrolling. We started with a simpler task. We're saying that, okay, assuming that the poachers are following some heuristic behavior model, and we know that behavior model ahead of time, then in this case, this becomes actually a reinforcement learning task, because from the ranger's perspective, poacher is just part of the environment. The ranger just needs to decide, given my current observation and my past observation, which direction should I go next? So we built this deep Q learning-based method to compute the ranger's strategy against such a poacher. Here, we have this Q network, which takes as input the observations of footprints, the animal density distribution, and a bunch of other information that the ranger can get. And then the output of this Q network is going to be just the Q values for taking different actions. Here we only have 5 different actions going up, down, left, or right, and standing still. And of course, after extensive training, this Q network hopefully can represent like some promising scores and tells us whether it is more beneficial to go to each of these potential directions. And that can help the rangers to decide what action to take given under any circumstances. So here's the result that we see. The training result indeed show that we can find a reasonable patrol strategy for the ranger. Well, the strategy is that the ranger starts from the patrol post and trying to go to the perimeter of the area and then trying to patrol along the perimeter until it sees something like footprints or other signs. However, this strategy is highly exploitable because the poachers the rangers always start from the patrol post and then go to the right and then go down and until it sees something. So if the poacher is smart enough, then the poacher might observe that there's lack of randomness still in the patrol strategy and can counter that. Then how can we handle this weakness? Leveraging what we have learned in the security games, we know that it is important to randomize. So we want a randomized policy for the defender. And how can we create such a randomized policy? We are treating a deterministic deep Q network policy for the ranger as just a single possible policy. And we're going to randomize over multiple deep Q network represented policies. So leveraging the double oracle framework for solving large-scale zero-sum games, and also the policy space response oracle framework in multi-agent reinforcement learning, we treat a deep Q network as a single action that can be taken by the players. And our goal now is to find a randomized policy, which is a probability distribution over multiple deep Q networks. To do so, we will start with 2 small sets of deep Q networks for the ranger and the poachers separately. Each might contain only 2 or 3 Q networks. So here in this example, we start with 3 Q networks for the ranger and 3 for the poacher. And we call them GD and GA, and we compute the Nash equilibrium using this current set of deep Q networks, and then train a new deep Q network that best responds to the other player's current equilibrium strategy. And these new deep Q networks will be added to the set, and then we can go back to the computation step to compute the equilibrium for this enlarged game. And we can continue doing this until at some point we are satisfied with the strategy we found and then terminates. So this is a nice framework, but a challenge here is that it might take too many iterations to get something that is reasonable. And even one iteration requires the training of a DeepQ network, which takes a lot of time. So we were thinking about how can we improve this. The first idea that we had is to use local modes for efficient training. We know that in the original problem, the poacher might get into the grid from multiple locations, like each of these 4 corners of the grid can be the entry points of the poachers. Now, for the local modes, we're going to restrict the poachers to enter the grid from a specific entry point. For example, in this local mode, we restrict the poacher to enter the grid from the upper left corner. And then in this local mode, we restrict the poacher to enter the grid from the lower right corner. And then the training in these local modes will be more efficient compared to the original problem. And we can train the agent in multiple local modes in parallel. At the end of the local mode training, what we're going to get is a few DeepQ network represented policies for the defenders, for the rangers, and for the poachers, which are good in the local modes. That's fine. We're going to leverage these reasonable policies in the local mode and use them as a starting point for the training in the original problem. So we're kind of treating them as a warm start for the iterative process for this double oracle framework. So in other words, and in addition to this local modes, we also found that we can use some domain-specific heuristic strategies to warm up the process. So if we put things together, what we're going to do is that at the very beginning, we're going to use our domain knowledge to get some heuristic strategies that we believe are reasonable to start with. And then we're going to send these initial set of strategies to each of these local modes, where in each of the local modes, we're going to run this double oracle type of framework, but restricting the poacher to enter the grid cell, a grid from one of the entry points. And we train for several iterations, and we get a bunch of different render strategies and poacher strategies for each of this global mode, and we call them these strategies as GTK. And then we combine all the strategies together to be this GT, and then we continue the training in the global mode. And then after a few more iterations of training, we output the defender strategy at the end of it. So what we found is that with this training paradigm, we can have a way to get a defender strategy that is more scalable than counterfactual regret minimization, and also leads to a better solution quality than the vanilla version of the policy space response oracle, meaning the vanilla version of double oracle applied to the Markov game case. So that's what we learned from this one. How can we deal with the real-time information? The second challenge that we found from the real world is that we need to do robust sequential patrol planning. Why is that? So we analyzed the data from the Queen Elizabeth National Park in Uganda, and we found that the patrol strategies used in one time period would indeed have impact on poachers' behavior in the future. And also, the wildlife distribution might change due to the past poaching activities, and that would impact the future poaching. This leads us to think that we probably should not consider the patrol planning as a one-shot planning problem. Instead, it is a sequential patrol planning problem, because whatever patrol strategy we choose now would have an impact in the future. On the other hand, we also noticed that in using our previous method, we need the poacher's behavior model, but the data we have is still quite limited. That means our estimation of the poacher's behavior might not be very accurate. And also, the poacher's behavior model might change over time. So how can we deal with such uncertainty in this domain? We need something that is more robust. So we turn from just sequential planning to this robust sequential planning. More formally, we're dealing with a problem where we have n targets, And we want to come up with a patrol strategy that is a mapping from state to actions, where here the state, it is described as the previous actions we have taken, where action here is like the patrol effort that we decided to spend in the last time period. And then also the state includes the wildlife density and the current time. The actions here is describing how much patrol effort will be spent on each of the targets. We assume that the poacher's behavior model is known, but there is an uncertainty in the model. So we here consider a uncertainty region, saying that we have these parameters in this uncertainty region. We don't know exactly the values of these parameters. Our goal is to learn a policy that can minimize the maximum regret, which is defined as we're trying to find out a policy pi such that we can maximize this regret, defined as the difference between these two quantities. The first quantity is the reward for the ranger when we know the parameter, the environment parameter is z, and we choose the policy that is best against z. So this pi star z representing the optimal policy given the environment parameter z. And the second quantity is the reward of using my current policy, or the actual environment parameter is z. So that is like, if we choose my policy pi and the environment parameter is actually z, then how much should I regret comparing to the best policy in hindsight, which is pi star z? And then we consider the worst case among all possible uncertain parameters, and then we choose the policy pi that can minimize this worst case performance, worst case regret. If we look at this formula from a different angle, then this can also be viewed as a zero-sum game between the planner and the nature, where the planner is choosing the policy pi and the nature is choosing the parameter z and the alternative policy pi hat, where the best alternative policy pi hat would be the pi star z. And again, in such a zero-sum game, any deterministic choice can be easily exploited, and we again want to use a randomized policy. So we propose this mirror algorithm, which is still following this double oracle or the policy space response oracle framework, but this time we are going to solve a max regret game. So in every step, we construct this game between the planner and the nature, where the actions for the planner could be just different policies, and the actions for the nature could be the parameter values plus the alternative policy. And we compute the Nash equilibrium of this game, and then try to learn the best responses against the other player's equilibrium strategy. And we added this newly learned best responses to the game, and we get a enlarged game and come to solve the game again. After a few iterations, we can terminate the process and output the strategy for the planner, which is going to be this robust policy. So we compared this mirror algorithm with several other possible approaches for choosing the policy to use, and we can see that the regret of using mirror is lowest comparing to the other approaches. So here, the maximum reward means that we are going to choose a policy that maximizes the worst nature's choice. So this is like the most conservative choice of the policies, while the middle means that we're given the parameter uncertainty region. So we're going to choose the middle value in that uncertainty region and treat that as ground truth to pick our patrol policy. And then random is that we're going to randomly sample a value in the uncertainty region and then plan against that. So this is to show that when we use this mirror approach, trying to find out a robust strategy and make patrol planning sequentially, we can indeed achieve this strategy that is achieving a low regret overall. So that's the second challenge that we face and how we handled it. The third one is the repeated interaction when there is an unknown attacker. This is actually motivated by the problem in a slightly related, but not exactly the security domains that we just mentioned. This is in the cybersecurity domain. Because in cybersecurity domain, it is very often that we face this diverse group of attackers, and these attackers have varying sophistication and their intent is unknown to the defender. And also in cyber security, it is more likely that the defender and attacker may have repeated interaction. That means the defender can infer from the attacker's previous actions and plan the defense accordingly. While on the other hand, the attacker knows exactly what kind of type they are, so the attacker can plan the actions based on their own type, but they also know that if they take some action, it might reveal information to the defender. So they may need to take actions in a careful way to maintain such informational advantage. And as a result, this becomes a sequential decision-making problem on both sides, comparing to the one-shot security game model that we had in the earlier models. So formally, we consider such a model where we have T-round game between the defender and attacker. And in each round, the defender can allocate K resources to N targets, while in each round, the attacker can choose one target to attack. And attacker has a certain type. The reward for the attacker to successfully attacking a target is actually determined by his type, where the type is unknown to the defender. The defender only knows a prior probability distribution over these multiple types. And the goal here for the defender, for us, is to find something that is closer to the perfect Bayesian Nash equilibrium. Because given the such sequential interaction, just the Nash equilibrium concept would lead to uncredible threat. So we want to enforce that the strategy we found is still good from any decision point onwards. And actually, there has been some work that uses mathematical programming to solve this problem. However, as we can expect, the mathematical programming-based approach cannot really solve large-scale problems. It can not even solve problems with the number of targets being larger or equal than 8. So to tackle this problem in a more scalable way, we decided to use a reinforcement learning-based approach. We proposed this temporal-induced self-play that is built upon 4 main ideas. The first is using a belief-based representation. The second is use backward induction. And third is policy learning. And the last one is belief space approximation. We're going to go through these ideas one by one. The first idea, belief-based representation, is quite straightforward. That is, instead of using a policy that maps the history to actions, we're going to use a policy that directly maps a belief to actions, where here the belief is your current belief of the probability distribution over attacker types. And such a belief-based representation can help in the case with long history, but the cost we need to pay is that in the execution or test time, we need to always infer the posterior belief after we observe the actions of the other players. The second idea, the backward induction, is also straightforward. We are going to have this reverse training process. We're going to train the strategy from the very last round all the way back to the very first round. And for each of the round, we will train a value network and a policy network. Sorry. And we're going to leverage the value network and policy network that have already been trained in the future round when we try to train our current round networks. And the benefit of doing this is that we don't need to sample the entire trajectory from round 0 all the way to round L-1, but we only need to sample one step trajectory from round L to round L+1. And in the actual implementation, we need to use a special reset function to help achieve this. And this also means that for every single round, we're going to use a separate network to represent the defender's policy. In fact, this can indeed lead to improve the performance. The third idea, the belief space approximation, is that, well, even if we're going to use a different network for different rounds, we cannot handle this for many, many different beliefs. How can we do this? We are going to sample k belief vectors and then train the strategy specifically conditioned on this particular belief and the particular round. And then if we want to query what policy should we use for a different belief, we're going to use this non-parametric approximation using the distance metrics between the queried belief and the sampled belief, and then to approximate the strategy that we can use. And the last part, the third part, the policy learning part, this is the last part. Yeah, the last part, the policy learning part, we can actually use different policy learning algorithms. For example, we can use policy gradient. In this case, we just need to update the network parameters in each training step. But comparing to the standard policy gradient steps, we need to take into account the beliefs, and we need to adjust the update rule a little bit. Instead of using policy gradient, we can also use regret matching to update our policies, where here we need to use the regret to update the policies. And by using this reinforcement learning based algorithm, we can solve games that are larger comparing to the mathematical programming based methods. And here, as we can see, the mathematical programming based methods can quickly run out of memory even when we have more than 8 targets or rounds, while we can handle those larger cases. And more importantly, our algorithm can generalize to more general game settings, not restricted to this repeated security game setting. We can have this grid world games, and we can use our algorithm to solve it as well. So this is like the benefit that we get by using the reinforcement learning algorithm. But of course, comparing to the mathematical programming based approach, this reinforcement learning based methods can find policies that are not as good as the mathematical programming ones if the game scale is small enough. So hopefully by now I've illustrated a few ways that we use reinforcement learning for solving complex security games. And there still exist several general challenges for using RL for security games. One is to have those policies more interpretable and explainable, because in several security domains, it is important for the stakeholders to really understand what's going on and to be able to verify the policy before they deploy the policy. And also, using RL means that we need to build the simulator or simulation environment and then train the policies in that simulation environment. And inevitably, there will be a gap between the simulation and the real world. And how to deal with such gap is also a general challenge that we face. Also, even in these security domains, if we want to launch anything in the field, then we will face those human attackers. How can we incorporate the human behavior modeling into the RL framework is also something that we need to keep thinking about and improving upon. And I have to admit that for all these methods that we have introduced here that uses RL for security games, they are not deployed yet because of all these general challenges. And we're still trying to see how we can overcome these limitations and bring these more flexible policies to the real world. So here we have this reinforcement learning for the security game-like problems, but there are a lot more other problems exist in the real world, and it involves multiple agents, but it goes beyond such defender-attacker type of interaction. I'm generally interested in leveraging machine learning and game theory and optimization to solve those problems, or at least to help tackle those problems as well. So in the rest of the talk, I'm going to mention one specific problem, and I'm trying to invite people to discuss or brainstorm what we can potentially do there. This is the food rescue domain. We know that reducing food waste and ensuring food security is something that we always want to achieve. Then how can we leverage AI to help that? That's something that we want to tackle here. In Pittsburgh, we have a platform called 412 Food Rescue. It rescues good food by connecting restaurants, grocery stores, or cafes that have perfectly good but not saleable food with local communities in need of food, for example, single mom shelters. And the platform relies on the volunteers to deliver the food. So they have the smartphone app. It posts the food rescue request on the app, and the volunteers can then claim a rescue on the app and pick up the food from the donor and deliver it to the recipient organization. Some of these photos shown here are actually taken when I myself worked as a volunteer and delivered the food from CMU Cafe to a local community. In this problem, clearly there's no defender-attacker type of thing, but we still have a lot of decision makers involved, the donors, recipients, the volunteers, and the platform. We, in the past, decided to work on the specific interaction between the volunteer and the platform, because one pain point of the platform is that they are uncertain which kind of rescues will be claimed. And to help improve the claim rate of the rescues, they use this notification and intervention scheme. Once there's a rescue published on the smartphone app, they will send notifications to all the volunteers that lives in 5 miles of the pickup location. And they will wait for 15 minutes. If they don't have any volunteers to claim that rescue, they will then notify all the volunteers on the platform. And 60 minutes before the deadline of the pickup, if there's still no one claims it, they would have this human dispatcher jump in and try to call the volunteers or text the volunteers that they are familiar with and just to beg them to help with the rescue request. But of course, they don't have enough human dispatchers to handle these requests one by one. And also, they don't really want to send too many notifications to the volunteers, because that might make the volunteers get bored and even lose interest to help with any of these rescue requests in the future. So what we were doing here is that we're trying to see how we can provide better intervention and notification schemes to avoid excessive notification and also reduce the human dispatcher's workload. Well, the first idea we had is, okay, we are still following what they're doing now, but we're going to change these parameters in their current scheme. We're trying to find out the best values of X and Y and Z so that we can achieve something that is better. And more specifically, we formulate this as an optimization problem with the goal of minimizing the expected number of volunteer notifications and the expected number of human interventions, with this lambda parameter controlling the weight of these two. And we want to make sure that the claim rate is no less than their current claim rate. So we want to change the intervention scheme, but we don't want to do harm to the key indicator that they care about, the claim rate. So we solved this problem using branch and bound and leveraging the data that we have in the past. So by optimizing the scheme using data from May 2018 to December 2018 and testing on the data from January 2019 to May 2019, we found out 2 new intervention schemes that can bring benefit to them. We showed them, for example, this first one, the first intervention scheme, that if you send notifications to people within 5.5 miles of the pickup location and wait for 16.5 minutes and to send out the second wave, and having the human dispatcher jump in only 45 minutes before the deadline of the pickup time, then you can reduce the human intervention by 13% without really increase your notifications. And they were happy with this potential improvement, and they decided to deploy this intervention scheme since February 2020. And we collected and analyzed the data before and after the deployment of this new scheme. And as we all know, the outbreak of the COVID impacted people all around the world, starting from early 2020. And in Pittsburgh, the life here is impacted significantly since the beginning of March. So we separated the data before March and that after March. And as we can see here, the first row is is the old scheme, where the second and third row is like the new scheme. And what we observe is that after the new scheme is deployed, the claim rate goes up. The average time needed from publishing a rescue request to having a volunteer claim it goes down, and the average number of notifications sent is lower. This trend continues even after the COVID impacted the area. These preliminary results, they are promising, but also we know that there might exist many confounding factors. And to get a more confirmative claim, we would need controlled experiments. But at the same time, we feel like, well, we can do better than just changing the parameter values. So we propose this rescue-specific notification scheme to further improve the notification efficiency. We want to send the first wave notifications to volunteers that are more likely to claim the rescue. The idea we have is to treat the problem as a recommender system. We want to recommend volunteers to each new rescue request. So we train a neural network-based model that can predict whether a rescue will be claimed by a volunteer given the features of the rescue and the features of the volunteer. When a new rescue request comes in, we apply this trained model to all the volunteers with this rescue and send push notifications to the top K volunteers. This idea sounds promising, and we indeed find out it can improve the hit rate, meaning the chances that the first wave volunteers can claim the rescue. However, the caveat is that we found this learned model discovers some very active volunteers and keeps sending them notifications almost all the time. As we can see here, this small portion of the volunteers receives more than 1,000 notifications in the test time. So this is definitely not good. And to resolve this problem, we decided to combine machine learning and online planning. Rather than greedily taking the top K volunteers, we enforce some constraints such that each volunteer receives at most L notifications every day. And when a new rescue comes, we will project a set of future rescues based on historical data and then solve a mixed integer linear program subjected to the notification limit constraint to determine who to send the notifications to. And this resolves the overconcentration issue and achieves a hit ratio at top K of 0.65, which is still significantly higher than the current practice. So here, let me explain what is this hit ratio at top K. That means we send the first wave notifications to around 664 volunteers, and then we check what is the likelihood that we have one of the volunteers who got the notification claim the rescue just for the first batch of notifications, so that we don't need to send another wave of notification to all the volunteers. So that's the hit ratio at top K. And in fact, now we are working with 412 Food Rescue and trying to launch a controlled field test starting in weeks so that we can have a more systematic comparison with what we have done before and with this new notification scheme. And at the same time, we also think about like the longer term effect of this. Well, as we can see here, what we're doing is that we learn from historical data, we optimize the intervention or notification scheme, and then we want to deploy this new notification scheme. And during the deployment, we actually can collect more data, which we can use to further improve the learned model and improve the optimization. And however, if we look at this learn, optimize, deploy, and learn scheme, there are a bunch of challenges in general. For example, we don't really have a huge amount of data to start with. And also we know that the intervention we use, in this case, the notification scheme we use, would affect the data distribution. And also even the domain experts may not perfectly know what kind of objective they want to optimize. And how can we make this entire iterative process work better? We tried to think of ways to handle this. We have some initial ideas here. We propose this bandit data-driven optimization with a no-regret algorithm to determine which notification scheme to use in each step. Here, this is still an initial attempt to try to analyze this problem. There's no short-term plan to deploy this in the field yet, but also I think this is something that not only applies to food rescue, but applies to many other problems as well. We have this learn, optimize, deploy, and learn iterative process, and how can we deal with a bunch of challenges in this process? As I mentioned, we had some initial attempts to tackle this problem, but we do see a lot more open problems in this space. Previously, we worked on ride-sharing platform as well, and in those problems, we're saying, okay, we know the drivers are strategic. They would try to game the system no matter what pricing or dispatching scheme you're going to use, the platform is going to use. And that's because the drivers want to make more money. And in this case, we rely on the volunteers. Then do volunteers still try to game the system, especially when they know that we are determining the notification scheme based on their past behavior? And also, we want to see how can we better incentivize the volunteers without any payment, because this is completely nonprofit. How can we understand their incentives and then better incentivize them? And the last thing, as we mentioned, because of this sequential planning nature, because of this learn, optimize, deploy, and learn process, how can we come up with better ways to handle those practical challenges in the sequential planning? These are all problems that I think worth discussing, and I hope that will be people who are interested in these problems and would like to discuss with us. So that's it for what I would like to go over, and I'm happy to take questions and discuss with you guys.
Thank you very much, Faye. We're opening the floor to questions.
Hi. I have one question in particular with regards to the Stackelberg games that you use to model your security problems, I guess. In all of these settings, you assume that you can model basically your problem just using just by figuring out the right payoff functions for both the defender and this attacker. I was wondering if you ever considered actually also putting restrictions onto the action set of the defenders in your settings, so that maybe, of the attackers in your setting, so that maybe like the leader in the Stackelberg game could take actions such as to restrict the actions that the followers could take.
Yeah, that's a very good point. So it's like the defender not only can deploy the security resources, but can potentially impact the game structure in some sense, right?
Exactly. Yeah.
Yeah. So we actually had a paper on this. In that paper, we were talking about the defender having the capability of manipulating the payoff structure directly. So for example, this is actually true in some of the problems, like in wildlife conservation, for example, we do see the agencies would change the fine, the amount of the fine if the poacher get caught. So think about this, it's kind of like the defender is actually changing the payoff of the attackers as a way to try to reduce the attackers' utility, reduce the poaching activities. And also, Worldwide Fund for Nature or other conservation agencies, they would run campaigns trying to advertise that rhino horns comes from the same material as your nails, so there's no special effect of rhino horns, and trying to reduce the demand for rhino horns, and effectively that can reduce the attackers' reward even if they succeed in poaching the rhinos. So, like, of course, all these changes in the payoffs would would lead to a cost, and the defender can choose to pay some cost to change the game structure and then to allocate their defensive resources to patrol and to reduce the actual poaching activities. So we did some work there, and we found that indeed, even with some small budget on changing the game structure, the defender can win an advantage in this combat against the attackers. And we haven't thought specifically about restricting the action set, but I think that's also worth considering.
Okay, gotcha. Thank you very much.
Mhm.
Hi. I'm curious about the problem you raised of making your reinforcement learning strategies more interpretable or explainable.
Mhm.
I'm curious if you think the way forward is to explain the complicated inner workings of these DQNs and all of these policies that you learn, or if it's to train simpler strategies that are easier to explain in the first place.
Yeah, so that's very good. Yeah, that's a very good question. And recently we worked on a survey paper on interpretable reinforcement learning, and we found that people are trying hard on all these different directions. Some people are trying to say, oh, let's just have this policies that are easier to understand, like decision tree based policies. And then some other people say that, okay, I'm going to just come up with natural language based explanations for those very complicated neural network policies. I think there are people who are doing both. From my perspective, I would slightly lean towards focus on generating simpler policies first. And we have some ongoing work trying to coming up with more simpler, like decision tree based policies for multi-agent reinforcement learning. So that's what we think is a starting point. But of course, I think there's a lot more to do. It depends on the actual needs of the domain experts. Based on our interaction with the experts, at least for the wildlife conservation domain, it's easier to explain a decision tree to them. In fact, when we start building the behavior models of the poachers to make predictions of poaching activities, we started with the decision tree policies with a very shallow decision tree and explain to them that, okay, this decision tree says if the distance to the village is small and the animal density is high, then we predict there is a high poaching risk. So in this way, like the domain experts can understand there, and there's a trust built between them and the AI, and then it makes them to be like more open-minded to other more complicated models.
Okay.
So in your work on the RL for security games, was all the learning done offline, say with data that you collected before? Did you consider trying to use data that you saw online to update your policy in kind of an adaptive manner? Yeah,
that's a very good point. So the work that I introduced here in this talk are all based on the case where we build a simulator, and some of the parameters in the simulator is built upon historical data, but we are going to train the RL agent in the simulator and to get the policy and then deploy the policy. And how to combine this historical data and the actual data that we're going to get after we deploy it is something that we also considered. We had several banded learning based work to handle this. We're trying to say that can we just treat this as a banded learning problem where we try to have some initial strategy built upon historical data, but every time as we collect more data, we change our strategy slightly and then to deploy it and to collect more data. So that's something that we have considered a little bit. It's just slightly different framework. We considered banded learning instead of reinforced learning. I think that one also makes sense to me as a way to better make better use of both historical data and the online data per se.
Any other questions?
I just have a quick follow-up question to the reinforcement learning approach and explainability. Like, do you actually want the policy to be explainable? Doesn't that make it easier for the attacker to figure out? Like, you want it to be explainable for the defender, but not for the attacker. Isn't there some sort of tension between these, or they're equally, like, an explainable policy can be just as good as one that is not explainable?
I see. Yeah, that's a good point. Yeah, we haven't thought about that part yet. I think in the current formulation, several of the game models that we're considering is actually zero sum. So there's less concern if it is zero sum game, because we can try to make by increasing the defender's utility in the zero sum game, we're trying to say that even if the attacker knows what the defender is doing, they can only achieve this much. But in practice, I can see that the human attackers' understanding of the defender strategy might be imperfect. And how can we incorporate that such misunderstanding, or the gap in the attacker's understanding of the defender strategy and the actual defender strategy could be something that we're taking into account when we design the strategies for the defender.
Okay, I think that's it in terms of questions. Let's thank Faye once again. Thank you, Faye.
Thank you all. Georges, you're going to have a break, right?